Good morning everyone and welcome to Year 10 Physics. This is Lesson 1. We are looking at scalars and vectors, measurement and units. These are the foundations of physics. What do we do in physics? In physics we measure. In physics we care about how much of a thing there is. In physics we care about relationships. But not just relationships. We want to know exactly how the relationships work. If this doubles, does that double or does it triple? In physics, we look for patterns. In physics, we quantify. We try to figure out what amount of something is there, and we always look for the units. When we quantify, to break it into really simple terms, we say that there are two different types of quantities. There are scalar quantities and there are vector quantities. Scalar quantities are those quantities that have a magnitude, they have a number, they have a unit, but they don't have a direction. They don't have a direction. For example, his mass was 86 kilograms. There's no direction involved that. He has travelled 14 kilometres to get here. There's no direction involved in that. Vectors, on the other hand, are those quantities which have both a magnitude, but they also have a direction. Now, the magnitude would always have units. The units actually really matter. The units are really important. Grams are not kilograms. Kilograms are not grams, okay? When we think about vector quantities, an example is he pushed the bobsled with a force of 300 newtons south. He didn't push it north, he didn't push it west, he pushed it south. He was born 3,900 kilometres east of here. He was born. There's a magnitude, 3,900 kilometres. There's a direction, east. When we start talking about scalar and vector quantities, here are some examples of each of them. Distance, speed, mass, time, area, volume, energy. All of these things are scalar quantities as far as we're concerned in Year 10. What about some vector quantities? Displacement, velocity, acceleration, force, weight, momentum. That's a Year 11 concept. Okay, we're going to learn about Newton's laws of motion in the next lesson. And Newton's first law of motion, the law of inertia, that's linked to momentum. So is Newton's second law, that's linked to momentum. But that's Year 11 content, so we won't do that today. Each of these vector quantities, displacement, velocity, acceleration, force, weight, momentum, all of these have magnitude, they have direction. They have magnitude, they have direction. Distance versus displacement. Okay, all of you have gotten here today by some means. You've come on your electric scooters, on your push bikes, in your cars, on the bus, in the train. I don't know, some of you walked here. But you didn't go in a straight line. There are no crows in this room as the crow flies. So there is some distance that you have travelled to get from your bed to that desk. The distance that you have travelled is it is guaranteed to be greater than the displacement that you have travelled today. So distance is that total length of path that you have travelled. So if I go for a bit of a wander around the room, so if you have a look here, I'm going to start, here I go, I'm going to go on a journey. You ready for it? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For the sake of the video, I've taken 10 steps at roughly 1 metre, not exactly, but roughly 1 metre each. I started in the front corner of the room. I'm now diagonally in the opposite corner of the room at the back of the room. I'm going to keep counting. 11, 12, 13, 14, 15, 16, 17. I'm at the front of the room again, but not in the same corner I started at. What number did I get up to? 17, 18, 19, 20, 21. 21 metres. The distance travelled, 21 metres-ish. You know, give or take 2 or 3 metres, because my steps aren't exactly 1 metre. What's my displacement? 0. Absolutely 0. Displacement will always have a direction. Displacement will always have a magnitude. It is always a straight line as the bird or as the crow flies. When we're finding displacement, some of the things that we are interested in for displacement, we are interested in having direction. We will do these sorts of activities using diagrams. On the screen before you now, you see a diagram. The diagram will always have an orientation. In this particular graphic, you see the orientation is north, south, east, and west. It doesn't have to be north, south, east, and west. It can be up, down, left, and right. It can be up, down, east, and west. It can be up, down, north, and south. But we will usually have an orientation. The orientation will usually take the form of a cross, where you've got two dimensions, and those two dimensions are perpendicular to each other. There will be a scale in your diagrams. You're going to do an activity for me later on today where you'll get to do some diagrams, and there will be a scale that I give you, and I say that the scale will be 1 centimetre is 100 metres, or 1 centimetre is 100 newtons. The physicist tries to scale their diagrams accurately. We're not that stressed as long as the numbers are pretty good. But the examiner will look at your diagrams and mark you for diagrams. In your Year 12 WACE exam for physics, if you're interested, there will be 180 marks. At least 5 of them are going to be with vector diagrams. This is an example of a vector diagram here. They're the easiest marks you'll ever get. The rest of the exam is very hard, but these bits are easy. So with our vector diagrams, we like to show the orientation, we like to show the vectors involved, we like to actually label the vectors with quantities, 400 metres east, 300 metres north. Finding displacement graphically. You're going to do this for me in a little bit. When we go to find displacement graphically, we draw out our vectors, add them together, tail to head, tail to head, tail to head, and then we draw what we call the resultant vector. In this diagram, the displacement vector is the resultant vector. We draw the resultant vector from the tail of the first vector to the head of the last vector. Then we get out our ruler, we measure it, and if we've scaled it correctly, we will have the answer. Finding displacement for journeys, mathematically, one dimension. Select one dimension to be positive. Here we see a journey. The person is moving east and west. They're not moving south and they're not moving north. They're only moving with values of east and west. Finding the displacement for this particular type of activity, we draw out our vectors, tail to head, tail to head. We draw the resultant vector from the tail of the first vector to the head of the last vector. And we can just measure the answer if we want to. But we can also figure it out mathematically. When you go to add vectors mathematically in one dimension, you have to decide, is east positive or is west positive? In this particular example, I decided that east was positive. So when we go to add the vectors together, we add together 500, positive 500 metres. And then we add negative 300 metres. Because although that person travelled 300 metres west, positive 300 metres west, they travelled negative 300 metres east. So that's an example of adding up vectors mathematically. You can do it graphically with arrows. You can do it mathematically. If you see the word calculate, you have to do it mathematically. If you see the word graphically, draw the vector diagrams, you have to do it with diagrams. Finding displacement for journeys mathematically, 2 dimensions. Here's a simple example. 2 dimensions. We've got a whole bunch of different displacements, but they're all combinations of east-west, north-south. That's it. They're all perpendicular values of east-west, north-south. And they're all over the shop there. S1, S2, S3. We love to label our vectors with subscripts, S1, S2, S3. But we could do this mathematically a lot easier because at the moment they're drawn on the page in the order that they occurred. We don't have to draw those vectors in the order they occurred. As long as the vectors are there, we can draw them in any order we wish. Why don't we draw them in this order? We've drawn all of the east-west vectors first, and then we've drawn all of the north-south vectors last. Mathematically, this makes it a lot easier. We find the total displacement east-west. We find the total displacement north-south. And then suddenly, it turns into a Pythagoras question. It turns into a trig question. Do you guys remember Pythagoras? The square of the hypotenuse is equal to the sum of the squares of the 2 other sides. And do you remember your trig? Sokotoa. So looking at this one, if I wanted to figure out the angle above the horizontal for that displacement vector, I'd say, right, I'd look at the theta, or the angle of theta just here, and I'd say, right, tan to the neg 1 of the opposite over the adjacent. Sokotoa. Finding displacement for journeys mathematically, 2 dimensions, simple. So that's the example on how to do it simply. You can go through and read those instructions, sketch out the given smaller displacements, arrange the smaller displacements into common dimensions, resolve each dimension separately, use the trigonometry to find the direction relative to the cardinal points, use your Pythagoras to find the actual displacement magnitude. Finding displacement for journeys mathematically 2 dimensions. This will not happen in year 10. But if you're curious, where would we go with this in year 11? We'd start giving you displacements that are not north-south, that are not east-west, but are some combinations of north, south, east and west. And then you have to figure out what we call component vectors. So that's where we go in year 11. But this is not a year 10 thing. You see the smiley face there? Smiley face says, don't do that year 10. Okay, so it won't happen. Don't worry about that. All right, moving on to the second part of this activity, measurement and units. Physics is based on experimental observations, quantitative measures. In order to have meaning across the globe, physics, like all science, requires a system of units common to the subject. Now, what we mean by that is, if I say 20 metres, they know what I'm talking about in Kyoto. They know what I'm talking about in Vienna. If I say 20 feet, they do not know what I'm talking about in London. They work in metres over there. We work in metres over here. In science and in physics, we always use SI units. These are the common units that everyone in science uses. These are the main SI units. You will get used to these. Metres, seconds, kilograms, amps, kelvins, moles, candelas. We know a bunch of these. We know what a mole is, don't we? We did that last term. We know what a Kelvin is. Well, maybe you do, maybe you don't. It's one of the first things we do in year 11. You learned about amps in year 9. So these are the units that we use. Types of quantities. There are the units that we have. Distance and displacement both use metres. Speed and velocity both use metres per second. We can use kilometres per hour. We can, but we have to convert it to metres a second. Prefixes and conversion factors. The tables here on the screen, you already know kilo means 1,000. You probably know mega means 1,000,000. You probably know centa means divide by 100. You probably know milli means divide by 1,000. When you did microscopes in year 8, you learnt about micro means divide by 1,000,000. Do you know all the prefixes? We will give you most of them. Here are some others. Exa and peta. Femto and atto. Too hard. Not us.